Welcome back. Today's topic 2, video 2, is over chemical reactions. Brief introduction. In this video, we're not really looking at specific chemical reactions, but some generalized knowledge that will help you recognize and hopefully understand chemical reactions. Here we go. When you're looking at chemical reactions, you have to understand the language they're written in. Chemical shorthand is basically an abbreviated mathematic system that tells us what's going on in a chemical reaction, what atoms are present, how many of each atom are present. It's just an easy way to recognize what's going on. It's all math, and it's all ratios and fractions. So if you're good at that type of stuff, this should be relatively easy to you. As you probably remember, each element has a symbol or a letter sequence that's associated with it. For example, carbon is the capital C, and oxygen is capital O, tungsten is capital W, calcium is capital C, lowercase a. Each chemical element has a chemical symbol associated with it, and as of right now, there are 118 unique chemical elements, the majority of which have chemical symbols associated with them. The more experimental ones, they are currently debated upon what the symbol should be because scientists like to get credit, and credit is often disputed. So, what you're seeing now is the periodic table. This is the easiest way to find the chemical symbols and a variety of other informations that might be useful to you. For example, up here in the top left-hand corner, if I can activate my, there we go. This is hydrogen. Hydrogen is the capital H. Hydrogen is the most abundant element. Over here is helium. The only difference between helium and hydrogen is one proton, but it is different enough that it gets its own symbol. Helium is capital He. When you're writing a chemical symbol, much like this one right here, lithium, if it's a single letter, like in oxygen, that letter is capitalized. If it's more than one letter, like in lithium, the first letter is capitalized and the second is lowercase. That helps when you're writing chemical compounds. For example, LiO is lithium oxide. If for some reason you write it incorrectly and you capitalize it all, LiO, that's not lithium oxide. That's lithium iodide oxide, because iodine is capital I. So it's very important that you represent the letters in the correct way when you're writing a chemical formula. Formulas are basically our way of recognizing and our way of representing different elements. Not all substances are composed of single elements. You should know that. There are only 118 elements, and there are billions upon billions of different types of compounds, all of which are formed from those 118 elements. When elements combine, it's known as a compound. It's one of our buzzwords. It's one of those chemistry 101 basics. You have to know what a compound is. And compounds are represented by unique chemical formulas, which is a combination of elemental symbols and numbers. This is a chemical formula. This is the chemical formula for glucose. Glucose. Glucose is a sugar. Glucose is the sugar that we primarily use as an energy source. Glucose has the chemical formula C6H12O6. What that tells us, and what this chemical formula is designed to tell us, is there are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen. Glucose has this exact amount of atoms and in that exact ratio. If I take away one oxygen, make it 5 oxygens, it's no longer glucose. It's something completely different. It has completely different chemical properties. So it's always important to represent your chemical compounds and your chemical formulas correctly. When compounds form, that's called a chemical reaction. Reactions are basically the process of changing either an element or a group of elements and changing the way they're arranged. You don't just create elements out of nowhere. You don't create atoms out of nowhere. You can't destroy atoms. You just rearrange them. This is called a chemical reaction. Chemical reactions involve changing the phase of at least one group of atoms. Remember, the phase is the unique chemical existence of a compound or an element. What you see on the screen in front of you is a chemical reaction. You have hydrogen. In fact, you have H2, which is hydrogen gas. Hydrogen is a diatomic, which means it exists as 2 atoms bonded together. And you've got oxygen, also O2, because oxygen is diatomic. It exists in nature as 2 atoms bonded together. Hydrogen is indeed a gas. Oxygen is a gas. And when they combine and when they react with each other, you get water. And hopefully you know water is a liquid. That is a very different physical property than the 2 atoms that make it up. Chemical reactions yield new compounds. You can get something completely different from the same atoms, just rearranged in a new way. Once again, our chemical formulas tell us everything we need to know. We know we have hydrogen, which is right here. That hydrogen has 2 atoms per molecule. We have oxygen, which is 2 atoms per molecule. And we have water, which is 2 hydrogens and 1 oxygen per molecule. These bigger numbers in front of the molecule are known as coefficients. These coefficients coefficients tell us the number of molecules we need for the reaction to occur. So we need 2 molecules of H2, 1 molecule of O2, and that produces 2 molecules of H2O. What that tells us is we have 2 times 2, 4 atoms of hydrogen, 2 atoms of oxygen. They rearrange and you get 2 times 2, 4 atoms of hydrogen, and 2 times, if there's not a number there, that's a 1. 2 times 1 is 2, so 2 atoms of oxygen. Once again, it's basic math. Now, when you're performing chemical reactions, sometimes you'll deal with something called a catalyst. I'm not going to speak a whole lot about catalyst right now, but it is a word that you need to be familiar with for future lectures. Catalysts are spectator molecules. They just watch what's going on. They're not involved per se. They're not used up. They're still present after, but what they do is they speed up the chemical reaction. They reduce the amount of energy needed for that chemical reaction to happen. Catalysts are great to make things happen faster than when they normally would. For example, we add enzymes to certain materials to break them down faster, like a cleaning agent such as, laundry detergent. We add laundry detergent to our clothing to speed up the cleaning process. We could clean it in water. It just wouldn't come out as well. Enzymes are your most common catalyst. There are a few other inorganic catalysts, but for the most part, we deal with enzymes. So, how do you recognize a chemical reaction? Chemical reactions occur all the time, and we don't always recognize them. We've got to train ourselves to start looking for chemical reactions. And the best way to look for them is to look for a change in the physical properties of the elements. Most things have a color. Most things have a texture and even an aroma. If these things change, more than likely, not all the time, but more than likely, a chemical reaction has occurred. For example, copper, as most of you know, is the stuff that plates our pennies. It's that pretty goldish color. It's not gold, but it's shiny and it's brownish and it's pretty. When copper reacts with oxygen, it turns green. So that color change indicated that a chemical reaction has occurred, and that green color represents a new compound. In fact, that's why the Statue of Liberty is green, because it's made of copper. As I mentioned earlier, you can't create matter, and matter are atoms. You can only rearrange it. You can't destroy it either. Same thing with energy. Energy can't be created or destroyed, so it can only be rearranged. This is an important concept when you're dealing with chemical reactions. Anything you put in a chemical reaction, if you put in 5 grams total of anything, after the reaction, you've got to get 5 grams back. It just doesn't disappear. The same thing with energy. If you put in 500 joules of power, you're going to get 500 joules of power on the other side. It might be in a different form, it might be heat, it might be a different type of energy, but it's still present. Einstein was the man. Einstein had it all figured out. Einstein figured out that mass and energy are basically the same thing, and that's why when I say conservation law, it's not the law. I don't refer to it as the law of conservation of mass and the law of conservation of energy, because energy and mass are equal thanks to Einstein. And Einstein said that energy is equal to mass multiplied by the speed of light squared. That's c. C is the speed of light. And because of that, if you can't destroy energy and you can't destroy mass, and you can't create energy or you can't create mass, it can only be rearranged. The two are interchangeable to an extent. Now, it takes a process to get energy into mass and mass back to energy, but it's possible, thanks to Einstein. Now, I always like to end on a joke, as you probably figured out. I think I forgot to do this in my last one, but how often do you like jokes about chemistry? Personally, I like them periodically. See you next time.